Okay, so I'm going to kick us off here. Thank you all for sticking around for the Friday night or Friday afternoon keynote session. I am very excited to introduce Dr. Stephen Townsend. He is an associate professor of chemistry at Vanderbilt University. He originally hails from the east side of Detroit and received his bachelor's degree from Oakland University, where he conducted research on the synthesis of nucleoside radical precursors. He received his PhD from Vanderbilt University, where he worked on small molecule total synthesis. In particular, he worked on tackling the infamous terpene BSK. He then went on to do a postdoc at Memorial Sloan Kettering and Columbia University with Professor Sam Danishevsky. And there he worked on the total synthesis of erythropoietin, peptide ligation, and Diels-Alder methodology. Since 2014, Steve established his independent program at Vanderbilt University, where he leverages organic chemistry to address problems in human health, particularly in the areas of human milk science, irritable bowel diseases, antimicrobial agents, and chemotherapeutics. Steve and his team have received a number of awards, including most recently the Camille Dreyfus Teacher Scholar Award, the ACS Infectious Disease Young Investigator Awards. He's been awarded an Alfred P. Sloan Fellowship and was also named the CNE News Talented 12. His dedication to education has also been highlighted by the Jeff Nordis Award for Excellence in Undergraduate Teaching. I personally met Steve while doing my PhD at Vanderbilt and can really attest to his dedication to his students and his mentoring skills. And I'm very excited to hear about this update on science and life. All right, Steve, I'll hand it over to you to take it away.
All right, well, I appreciate the very kind introduction and the invitation to speak with everyone today a little bit about our research program and I guess the life behind the research program. I remember in 2014 when I started, the first time I went into a classroom, I was telling the students that I had a young daughter at the time, and one of the students was like, I didn't realize that like professors have an actual life. So that was kind of weird, but I think that's important, to really show people that professors are also humans too. So I guess to begin this talk, I'm going to talk a little bit about my background and then show how I got into the academy, and then ultimately talk a little bit about the project, which was the centerpiece of the dossier that got our lab tenure. So when it comes to family, as Jade said, I'm from Detroit, Michigan. This is an aerial picture of the D, and so Detroit is fantastic, but it's also really cool in that we're the only city in the United States that sits exactly due north of Canada. So although this is a forward-looking picture, in the background is actually Canada, and that's south. Okay, so it's pretty cool, Windsor. Now, I grew up on the east side. I'm the oldest of 5 siblings in a single-parent home. My mom is really a hilarious woman with a hilarious life. If I take you back to 1983, she's in ROTC. My mom probably has the best eyesight out of anyone I've ever met. She's also a sharpshooter. So if you put 50 targets 100 yards away, she'll hit all 50. But because of that, she signed up to go to the military, and she realized at some point, oh, I don't want to go to the military. How do I get out of this? And the person who she enlisted with said, well, you're coming unless you have a baby. So cue up Steve Townsend, and that is the story of my famous birth. So these are my siblings and my mom, of course, in this picture. Our family, right, sort of interesting family where, all of the women, I guess, always work and are functioning members of society. And all of the dudes typically go to jail. So I think there's only 2 of us in my entire family, 2 men that have not done time in prison. And indeed, this is a picture of me visiting my Uncle Jerry when I was about 9 or 10 years old. So that's sort of just the reality of the situation. But what I show you to the far left is my family, I think 19 years ago. This is a picture of us like 3 years ago and about 300 pounds heavier. So that's also just a part of reality. Now, growing up in the city, I think everybody recognizes that it comes with its own challenges. My mom always sent us down to Tennessee for the summer because she always wanted us to understand the value of hard work. So, when I was 12, 13 years old, I was picking tobacco and picking cotton in Tennessee. in order just to really understand what it meant to do actual hard manual labor. What I show you here is one of the plantations that I've in the past picked tobacco on. It also turns out that this is the plantation that my family descends from. So we're part of the, less than 1% of Black people in the country who know the plantation that they descended from, right? My family can actually trace back to Africa, which is a little bit uncommon because most plantations destroyed all records. So this is Wessington Plantation, 40 minutes north of Nashville in 1932. This is a picture that was taken like 3 or 4 years ago. And so I've been to this plantation like 100 times. I know it like the back of my hand, and it's pretty cool. I also know my great, 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 great grandfather and grandmother. And this is really where the story of chemistry begins. My great, 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 great grandfather, Emmanuel, was the head chef of the plantation, and he was also a chemist. So, in the family, it's a nice running joke that, the chemistry sort of gene maybe traveled 4 or 5 generations from him to me. Now, after learning a lot about these people that you see in this picture, basically every summer of my life until I was 18 years old, I went on to chemistry or to do chemistry in college. So I graduated from King High School in Detroit, moved to Oakland University, and this is a crazy year because this is the 20th anniversary of the first reaction that I ever ran as an undergraduate. That was back in September of 2001. I worked for Kathy Moore, who was a biochemist. I was the lone organic chemistry person in her group. At the end of the first year, she told me, I think you probably are going to be headed toward graduate school, and I can teach you a lot and I can help you get there. But what she was concerned with was whether or not she could teach me how to exist as a Black scientist in chemistry. So she had me transferred to Amanda Bryan Friedrich's lab, who is now currently the dean of the graduate school at Wayne State in Detroit. And I worked with Amanda for about 3.5 years. So that was sort of an experience that really fundamentally changed my life. I set my first hood on fire in Amanda's lab, and she didn't fire me. So I learned that when students set something on fire in lab, right, you should take care of them. All from Amanda. Now, in addition to working for Kathy and Amanda, I met Latoya back when we were undergraduates. We did not have any children at the time, but this is a picture of Allie and Angela last weekend. So all of the gray hair that's on my face is not because of the tenure process, it's because of these two. Now from Oakland, I was a senior, and I remember I was running a column, and Amanda came in the lab and she was like, have you decided what graduate school you're going to go to? And I was like, I'm going to graduate school. It was sort of like news to me. So I remember it was like 5 days before the deadline for most applications. I took the GRE and then applied. And then eventually, after all the dust settled, decided to go to Vanderbilt, where Gary Solokowski was moving from Texas A&M. So this is Belshazzar-Skyson, the molecule that Jade mentioned earlier, great structure. But even more so than the chemistry that the chemistry skills that I developed as a graduate student, I think Vanderbilt really taught me the power of friendship with inside of chemistry. And so, I met a ton of people who I speak to this day. So this is Matt O'Reilly, who was a couple of years behind me. He's a professor at Villanova. And this is Stephen Chow, who's in charge of a manufacturing group at AbbVie in Chicago. So, I never take for granted the power of relationships. And I think that was really solidified when I was in graduate school. Now from there, as Jade mentioned, I moved on to Columbia and Sloan Kettering, where I work with Sam Danishevsky. Everything I know about when it comes to doing this job, I learned from Sam, whether it's writing a grant, writing a paper, right? How you should attempt to mentor every student differently because everyone has different needs. Sam is the man, and he taught me everything. He also reiterated and sort of reaffirmed the value of relationships because I was around the 500th trainee that he had in his career. And so, it's just powerful, right? When you have this many people who are all from the same family who can help you. So in this case, I show you a picture of when I was in Hong Kong. There were 200 people at this conference, and it was pretty crazy. Someone came to the mic and said, if you train with Sam Danishevsky, go to the hallway to take a picture. And about 9 people get up and go to the hallway. 8 of us in this picture, all professors. And then one person who took the picture, I'm not sure why she didn't get in the picture, but needless to say, people from this family are everywhere. And so again, this was a powerful moment and really reaffirmed, right, that I should have gone there to train, right? It was the right decision to do. Now from there, you got to find a job. And so this is where, things are a little bit crazy because, most people don't realize it, but when you are applying for a job, whether it's government or academia or big pharma, you don't really have a lot of control over where you're going to live. So it just so happened that I applied to 24 places. I got interviews from 4, and then I was fortunate to get 4 offers. But 3 of these places are in the Southeast, and 1 is in the desert in California. And I'm a kid from Detroit. So that was kind of crazy that, I was going to move back to the South. And ultimately, I moved back to Vanderbilt just because of the interdisciplinary environment. I knew that if we could make things as organic chemists, this was the place where you would be able to test them and really exploit the power of chemical biology. But that's just the start, right? Eventually, you have to work toward getting tenure. And most people, right, recognize this as being a very foggy process. Here, they simply tell you you need to have excellence in research, be effective in teaching, and have satisfactory service. And that is the only instructions that you actually get about what you need to do to get tenure. You don't know how many papers you need to get, how many grants. It's just like a very, very black box. But ultimately, you figure out that 70% of your tenure decision is how good of a researcher you are, 20% is how competent you are in teaching, and then 10% is serving on committees and making sure that the university can keep running. Now that gets us to the projects, and a lot of the captions on this slide are out of control because I was trying to repair these like 5 minutes ago and didn't do a good job. I'm actually missing, Alex's molecule on here. But needless to say, when I started projects for this group, I knew that we could do organic chemistry because that's what I do. It turns out I didn't really want that to be the centerpiece of the tenure document because I wanted to showcase that we could do things that we maybe don't know how to do. So at the moment, right, molecule after molecule is getting synthesized in the lab. We're publishing them and it's really fun. But where the group really started as sort of our start point as our centerpiece was with human milk science. And so I'm going to walk you through one of the human milk science projects and really show you where that began, how it began, and where it's at now. And then ultimately, this is really the reason that the lab was tenured. So most people who know me know that I'm a humanist. I'm an Aristotle fan, right? So I think art imitates life. If you are an Oscar Wildean type of person and you think life imitates art, I hope I did not offend you. In this case, I'm a postdoc. My wife just graduated from Columbia as a graduate student and she's pregnant. We're walking through Harlem, 125th Street, and next to the Apollo Theater, right, we see a bunch of advertisements for infant formula. Now, my lab does not do any shaming of formula use whatsoever. But I'll tell you, back then, this was a little bit strange to my wife and I because she was pregnant. And we knew just from the power of Google that in most countries in the world, you're actually not allowed to advertise infant formula, right? In some countries, it's illegal. But in the United States, in this very poor area of Manhattan, you see advertisements for Similac and other products. Now, you can sort of compare that to the rest of Manhattan, where I give you a nice little map that as you see darker shading, the value of the people who are there, right there, the amount of money they have increases. So all of those dark areas around Central Park, those are where millionaires and billionaires live. Coincidentally, this is also where New York City concentrates all of their lactation rooms, their lactation consultants, and all of their propaganda to promote breastfeeding. Interestingly, you don't see any of this type of imagery if you go to Chinatown, if you go to Spanish or Black areas of Northern Manhattan or the Bronx, or if you go to Eastern European areas in Queens and Brooklyn. Okay, you only see this type of stuff during or where the rich areas are. So, as a humanist, right, I of course want to know why is it that we target specific methods of feeding to people based on how they look and how much money they make. But I trained as an organic chemist and no one's going to pay me to do that. So the centerpiece of our project, as I was walking through Harlem, right, the very first thing that I wrote about was how we can dissect and pull apart the macromolecules in human milk and figure out how mom uses them to keep her baby healthy. And then ultimately, that would be our contribution to the taxpayer in the United States. So as we march forward and we think a little bit more about philosophy, right, this is sort of the basis of all projects. If you ask me what do we care about in our group, I would tell you every person in there whether they thought deeply about it or not, really cares about why people get sick. I think you can use that to sum up what we care about. And what we want to do to treat or fix sickness is just use chemistry, right? And that can be very broadly defined. For most of us, it means that we want to supply new drugs or we want to make new molecules to figure out what they do. There's some students in my group who typically make compounds that are used to prolong or fix the function of drugs that we already have, right? This can take you into the area of antimicrobial resistance, where we know a lot of antibiotics are broken. Well, in theory, we can make molecules to fix the function of broken antibiotics. And the last way that we try to apply chemistry to fixing sickness, again, I'm a humanist, so I got to quote Sun Tzu here from The Art of War, is that we try to beat our enemy without actually fighting them. And so there are a number of students in my group over time who have targeted virulence factors of bacteria, right? If we can prevent them from moving, we can prevent them from growing, right? So instead of actually directly killing them, killing bacteria and forcing them to evolve resistance against our compounds, we can defeat an infection another way, and that way we don't encourage resistance. All right, so with that being said, I'm going to take you on a little journey into a more recent problem that we've been interested in the group. I'm going to give you some background on premature birth as a problem. We're then going to go on a massive tangent, and then we're going to come back to the actual research that I want to present to you today, all from the 30,000-foot view. Regardless of what type of background you come from, you'll be able to follow what we're doing. So when we think of premature birth, it's pretty interesting. If I were to ask everyone who's in this session today, where do you think premature birth on Earth is the worst? Most people would probably say sub-Saharan Africa or Southeast Asia, because these are the worst health systems in the world. I think it would surprise most people to find out that the United States rivals many places in sub-Saharan Africa. I have a friend at Kansas State who's from the Congo, and she finds it just miraculous that the premature birth rate in the state of Tennessee is higher than the Congo. How does that happen? If we go ahead and look in state by state type of basis, it turns out that, well, yeah, we have a big problem. So if we go to the coast or the Northeast, these are places where you would not expect premature birth rates to be that high, and they are not. However, if we go to the Southeast of the United States, it turns out that things are pretty alarming. And sadly, Louisiana, Mississippi, and Alabama all have premature birth rates that are higher than most of sub-Saharan Africa and Southeast Asia. So what's the financial penalty? Well, it turns out, if we think about how many births there are per year, there's about 140 million. About 10% of those babies will be born premature. And then of all babies who die early in life, we can trace that back. It turns out about 17% of them were preemies. Now, interestingly, when we think about, again, the scope of this problem, it's about a $26 billion hit every year. It turns out, vaginal deliveries cost about 5 to 10K. If a baby is born by C-section, you can double that count, 8 to 15. But if we have a preemie, it turns out that that's about a $50,000 price tag when we consider all of the care that's going to take to make sure that that baby can survive. Okay, so this is a huge problem and one that's often ignored in this country. So if we go in and we do a little bit of a dive into some of the causes of premature birth, it turns out that you can divide these really into 3 categories, and then we're going to combine 2 of those categories into 1. So about 45% of preterm births are considered spontaneous preterm labor. We actually don't really understand how they happen, and because we can't find a cause, we lump them into that pot. About 30% of preterm births are actually caused by an infection, typically viral or bacterial, to mom or baby. And then the remaining 25% are caused by premature rupture of the membranes. So in more colloquial terms, we would just call that the water breaking. If you actually analyze why the water would break early, a number of those cases are due to a bacterial or viral infection. So in reality, about greater than half of all premature births are likely triggered by some type of infection, either to mom or baby. Our group is interested in one of the 2 leading causes of premature birth, and that's group B Streptococcus. The other is E. coli. It turns out that this is an image that was taken back when we first started working with the Gaddy Lab by Dorothy Ackerman, who was a student working with me, and Ryan Doster, who is a student working with our great collaborator, Jen Gaddy. Group B Strep is a fascinating species of bacteria. mainly because it's transient. So what that means is that it comes and goes over the course of our lives. Everybody who is in a seminar right now will have group B strep colonization somewhere between 7 and 10 times over your lifetime. And about half of the people in this virtual room have group B strep colonization right now. Now, it turns out that for most of us, group B strep colonization is not going to cause us any harm. It can actually function just as a symbiotic member of our microbiome. But for select populations, it can be rather lethal when we think about people who are elderly, people who are immunocompromised. And in this case, what we want to think about are women who are pregnant, because this can be very dangerous to their babies. So it turns out that if a baby contracts a group B strep infection from their mom, about 90% of those babies will present with sepsis or infection of the blood. 10% will present with meningitis. Now, interestingly, this is a problem that we actually know how to address pretty well in the West. About 11 countries specifically practice intrapartum antibiotic prophylaxis. So it turns out this is a picture of some mom who during week 35 is being evaluated for group B strep colonization. If she is group B strep positive, it turns out that's not actually going to be a problem. She'll just be given an antibiotic from the moment that the water breaks until the baby is delivered, regardless of how much time that takes. And that's typically going to prevent the infection. For most women, they will be given penicillin or ampicillin, but we know that beta-lactam use is not without its challenges. For those who are at low risk of anaphylaxis, you won't be given penicillin. You'll be given a next generation beta-lactam, such as cefazolin. If you're like my brother Chauncey, who is severely allergic to beta-lactams, you won't be given one. You'll be given clindamycin. And if the bacteria is not actually sensitive to Clindy, then you're going to be given vancomycin. And so this is, a lot more serious than it looks. When my wife was giving birth to our second daughter, it turns out that her suite mate in the delivery room needed an antibiotic, and they gave her vancomycin for about 22 hours. Okay. So, you can imagine that's going to prevent the group B strep infection from going from mom to baby. But what happens to all of the other bacteria in and on that mom if she's been given vancomycin for over 20 hours, right? She probably has no microbiome after she just delivered a baby. So this is a severe problem. And so once we learned about this in the group, Dorothy, Kelly, and I, we sat down and we started really deep diving into the use of antibiotics against group B strep. It turns out we use about 26 antibiotics in this country. Group B strep is only sensitive or can be killed by about 6 of them. So if we look at tetracyclines, very common antibiotics, you can't use them against group B strep. 85% of strains are resistant. Even though we use clindamycin in the clinic, 42% of strains are resistant to clindamycin. Way back in 1983, when my mom had me, she was given erythromycin to prevent group B strep transmission. We no longer use it in the clinic because the majority of strains are resistant. And then it turns out that antibiotics like aminoglycosides or antifolates do nothing to group B strep. They are 100% resistant. And so it was at this point in the game that Dorothy came to me and we started talking about the milk microbiome, because before that single day where she came in my office, we all for some reason thought that human milk was sterile, but it's not. There's about 700 species of bacteria in milk at any given time. What we noticed was that group B strep is actually a member of the milk microbiome. It's actually pretty common in mother's milk. But it turns out that babies that are consuming mother's milk are at a decreased risk for developing a group B strep infection, even if they're drinking group B strep, right? So that was kind of gnarly to think about. Now you can contrast that to those that are formula fed, and they're at an increased risk of developing a group B strep infection, even though infant formula is sterile. And so for all the trainees in the audience, this is how we formulated the first hypothesis of the program. There has to be some difference between human milk and then cow's milk. Cow's milk is the basis of infant formula. And ultimately, we wanted to figure out what those molecules were, because we believe that they can modulate group B strep. And so now we're off to the races. We need to figure out what these compounds are. Our first task was to compare human milk to cow's milk to figure out what's the difference. It turns out that this becomes really cool sort of evolution type bar humor and discussion, because these patterns that you see here are actually pretty firm. So for most animals, lactose is going to be the major macromolecule in milk. For most animals, unless you're a camel or a dolphin that lives in water, you're going to have about 32% fat in your milk. When it comes to very big animals like cows, they have a ton of protein. And this is an evolutionary mechanism because cows don't really have a defense mechanism, right? They're not going to scare anybody with their moo. So what they can do is get as big as possible, as quickly as possible. And they do that by having a ton of protein in their milk. Now, to contrast, it turns out that for primates, it's actually more important that our brains develop faster than our bodies. And so when you look at human milk, we have almost no protein. And in fact, most babies are protein intolerant. And as a replacement, what we have are complex oligosaccharides. They're known as human milk oligosaccharides. More broadly, we can think of them as primate oligosaccharides. But if we compare to cow's milk, there are really no complex oligosaccharides in cow's milk. Okay, so this is how we took an interest in studying the human milk oligosaccharides as really the centerpiece of our program. And we also got interested in learning about the oligosaccharides, the sugars, the complex sugars that are in other animals' milks. So much so that I have friends who are actually out there milking mice so that we can get some mass spectrometry and learn about what's in these samples. And so this is actually a process that was occurring in my friend's lab at Duke. This is kind of weird, but also kind of cute, I guess. If a mouse having anesthesia is cute. Now, when it comes to broadly, what animals have oligosaccharides in their milk and how many do they make? Well, it turns out there's not a lot of rhyme or reason to this. What I can tell you is that humans make the most oligosaccharides. We have 8 to 20 grams per liter of complex oligosaccharides in our milk, and we have about 200 unique oligosaccharides. Now, if we think more broadly about some other patterns that we can pull out, well, it turns out that animals that produce one baby at a time typically have more oligosaccharides in their milk. Generally, primates reign supreme. And then, of course, animals that feed for very short breastfeeding durations, such as bears or kangaroos, also have a lot of complex oligosaccharides in their milk. Okay, but otherwise, there's not too many patterns. And what I really want to draw your attention to on this particular table is the comparison between human and cow, right? Because bovine milk is what makes up formula. We have about 8 to 20. Bovine milk has about 0.1 to 1. And then we have about 5 times as many unique oligosaccharides. Okay, so these compounds are very special in human milk. All right, so for biosynthesis, we're not going to hit this too hard. I just want to show you how these compounds are made. They're produced in the mammary gland. They start with lactose because there's a lot of lactose present in human milk. There are enzymes that are in the mammary gland that can form polymers from lactose. And so they use N-acetylactosamine as a building block. And then once the synthesis of the sugar is complete, the enzymes use lacto and biose to stop the synthesis. And so that's going to produce either linear or branch structures. At this point in the game, all women are going to produce the same sort of core structural backbones. But based on your blood type, that's going to determine what type of fucosylating or sialylating enzymes that you have. Okay, so everyone, right? There's going to be 4 different sort of milk groups or blood types that we're concerned with. Different women are able to produce different enzymes that place fucose on sugars in different positions. Okay, similarly, we all have the ability to put sialic acid on different positions. Again, all based on blood type, right? So we won't go too far into this, but this is just to say that the syntheses of these compounds are actually pretty straightforward until it comes time to put fucose or sialic acid on the sugars, and then it gets really complex. How complex does it get? Well, it turns out, again, there's about 200 unique sugars that can be produced based on what your blood type is. They range to some that are very small, all the way up to some that are very large. And interestingly, they vary from mom to mom. So some women will produce as few as 25 sugars, some as many as 125. And what's really cool is that they change over the course of lactation. Now, for most people, if I say, what's the purpose of a sugar? 9 out of 10 are going to say it's for metabolism, right? We use these for carbon so that we can get energy. Well, it turns out in one of the sort of interesting feats of human evolution, mom spends about 300 to 500 calories per day in making these sugars, and her baby gets 0 calories from them. Okay, we do not metabolize them. We don't get energy from them. And in fact, we actually can't even digest them, period. They end up in the poop for the most part. So if that's the case, mom's making compounds, they're not for her baby. Who are they for? this is where our program starts to take off. And so we could talk about what these compounds were known to do before we started, what we discovered, and then ultimately how we're trying to apply this. I'll show you some interesting results from Rebecca Moore. So my good friends, the first effect that was known for these compounds way back in the mid-80s is that they are prebiotics, okay? They're fiber. Basically, mom uses these compounds to selectively grow good bacteria over bad bacteria. Why would you want to do that? Well, if you can selectively grow good bacteria, they can outpopulate and outcompete all bad bacteria. And then ultimately, that's one of the reasons why breastfed babies are so healthy. Okay. These compounds are also anti-adhesive antimicrobial agents. I think this is the dopest mechanism that they do. If you think about infections, right? It turns out that for a gut-based infection, right, if you got an E. coli infection, one of the early steps is that E. coli needs to bind to a sugar that's on your epithelium in order to recognize you as host and then start their infection. Well, because mom is brilliant, what she does is provide these milk oligosaccharides, which share structural homology with epithelial-bound glycans, right? So they look the same, these HMOs, as the sugars that are coating your epithelium. The bacteria don't know which is which. There are more HMOs present and free-flowing in the system. And so bad bacteria can bind these compounds and then just get titrated from the system. Now, our group, way back in, I guess, 2015, 16, and 17, discovered that these compounds were antimicrobial agents. So they have antibiotic-like properties. We can prevent the growth of gram-positive pathogens. And we also figured out that these compounds have antibiofilm properties, and this is across both gram-positive and gram-negative bacteria. All right, so at this point in the game, I'm going to jump right into some application because we've been able to do some really cool stuff with these compounds. And then, we'll take some questions and talk about anything that you want to talk about. So this gets us right back, finally to premature birth. And in more recent times, Rebecca Moore, who is currently lieutenant on this project, had an interesting hypothesis, and it was that she could use human milk oligosaccharides effectively to prevent premature birth, okay? And so the way that she envisioned doing this was that she wanted to use milk oligosaccharides to stop group B strep from sticking to gestational tissues, okay, to the fetal sac that the baby is in. If we think about things that cause premature birth, well, it turns out that pathogens adhering to the gestational sac or other tissues around the area where the baby is a common trigger for preterm birth. So her hypothesis was correct. If she could prevent this from occurring, you in theory could prevent premature birth overall. So to test this hypothesis, our collaborator Jen Gaddy was able to collect a fetal membrane from a woman who underwent a C-section over in our medical school. She handed it off to Rebecca, and Rebecca was first able to purify the surface of that tissue to make sure that there's no microorganisms growing. You then have to make sure you thoroughly wash the tissue so that you don't have any antimicrobial agents still present. At that point, what you're going to do is grow group B strep on that tissue, either in the presence of human milk oligosaccharides or absent human milk oligosaccharides, to see if those sugars can prevent the bacteria from sticking. And then you're going to process using single electron microscopy to actually see whether or not your hypothesis was correct or whether it was wrong. And then I believe for this particular sample, this number is off. I think it's donors from, or we pulled the milk of 5 different women in order to get human milk oligosaccharides. There were likely going to be about 180 unique structures in that sample. And so this is a pretty cool image of the fetal sac before the experiment. What you're looking at is the chorial side of the fetal sac that the baby is sitting in. It turns out that this is the interface between the sac and mom. And so this is completely covered with bacteria under normal circumstances, right? Bacteria are able to come and go as they please on this side. Now, what's really cool and maybe strange about human pregnancy is that if you just flip over that very thin membrane, you get to the amnion side, and this is the interface with the baby, and it's completely sterile, okay? So, if you go to the literature, you'll see a lot of debates about whether or not there are bacteria present in the womb. They are in the womb. They're just not on the inside where the baby's at. Okay, that's completely sterile. And in 2021, we have no evidence that there are bacteria inside the fetal sac with the baby. All right, now on the far left, you see a picture of a biofilm. This is after Rebecca grew up Group B Strep onto the surface of that fetal membrane. It turns out you can see beautiful microcolonies. The biofilm is protruding out of the screen toward us. And we can also see all of the lanes where the bacteria are tracking their resources. Now, if we just grow those microorganisms on the membrane in the presence of milk oligosaccharides, Rebecca got a blockbuster result. It turns out, yes, these sugars from human milk can prevent the bacteria from colonizing that surface. And thus one in theory can make the stretch, or at least provide evidence to say that these oligosaccharides could prevent prevent premature birth if that event is going to be caused by Group B Strep adhering to the fetal sac. Story number 2. So it turns out, if we go and we think about human pregnancy, I always call it weird and awesome because I think it really is both. When we think about mom being able to protect the baby when the baby's inside mom, she has a number of tools at her resources, and one of them are white blood cells or leukocytes. Well, it turns out that there's such thing as placental macrophage, which is basically a sentinel. It's patrolling the area around the baby to look for anything that's foreign so that it can engulf it and ultimately destroy it. One of the things that these macrophages look for are bacteria. And so it turns out this is not a singular event. The opposite is also true. A lot of microorganisms are heat-seeking missiles to try to find these macrophages in order to try to destroy them. And so in this sort of beautiful set of images that Rebecca was able to capture, we can see the warfare that's ongoing between a placental macrophage or a leukocyte and Group B Strep. Now on the far left, you see a bunch of stringy fibers popping out of that macrophage. Well, that's called an extracellular trap. And so ultimately what happens when a macrophage encounters a large swarm of bacteria is that it lyses itself. It undergoes a kamikaze mission and starts spitting DNA out left and right. All of those bacterial cells that you see in this picture are going to be dead because they're going to stick together. Unfortunately, that macrophage is also going to be dead. Now, when Rebecca showed me these images, I immediately hit the literature, and it turns out that the formation of extracellular traps is also a trigger for premature birth, right? Those fibrous DNAs protruding have some type of signaling that they do to launch premature birth. And so in the second set of experiments, Rebecca wanted to go in and see if she could use milk oligosaccharides to prevent the warfare that you see on the screen. Can you prevent Group B Strep and a macrophage from actually engaging in each other or engaging with each other? And that ultimately would prevent extracellular trap formation from occurring. And thus that would be another treatment for premature birth. So here you go. Rebecca was able to gather some placental macrophages and culture them with Group B Strep just by itself. And what you see is extracellular trap formation for basically every cell in this picture. If, however, you grow culture these placental macrophages in the presence of milk oligosaccharides, what we see is prevention of extracellular trap formation. All of those macrophages are generally intact, and we don't see the swarming of bacteria to that scene. Okay, so again, this was another check mark where Rebecca is able to clearly demonstrate that these milk oligosaccharides have the power to prevent specific events that can trigger premature birth. And so what we can do is go ahead and show a culmination experiment, right? That was really designed by Jen Gaddy, my beloved collaborator. And this is really the culmination of everything we tried to do with this program over the past 7 years, is actually demonstrate that we can take milk oligosaccharides and use them to prevent some other type of illness that has really nothing to do with breastfeeding. Okay. And so in this particular experiment, what we're going to see is if we can prevent Group B Strep transmission or premature birth in a cohort of mice. What we do first is breed the mice, right? And so they explained to me how this process worked, and it's pretty gnarly, where you take multiple mice in several pens. You then take like one boy mouse and you rub his back all over the girl mice. It's really strange. You then put that mouse aside and you bring in another dude mouse. And because dudes are like territorial morons, he breeds every girl mouse, and then you get a bunch of pregnancies, which you can confirm just days later, okay? So if we confirm pregnancies at day 0.5, we can move forward 2 weeks later, provide human milk oligosaccharide prophylaxis. So prophylaxis is preventative therapy, right? We're then going to go in the next day, and we're going to colonize all of these mice with Group B Strep who are pregnant. If between day 15.5 and day 16.5, as I've understood it from the literature, In a normal set of group B strep positive mice, they would all just start giving premature birth as a result of an infection. But from talking to the students and our great collaborator, it does not seem like that was occurring. And so as we keep going forward with the experiment, we can then treat these mice with milk oligosaccharides one final time, and then we have to sack the mice and evaluate whether or not the hypothesis was correct. Okay, can we prevent GBS transmission from mom to pup using milk oligosaccharides? And again, this is in a mouse model. And so the answer to the question becomes yes, to this tune of about a 40% reduction in the bacterial burden. So if you go in and you look at all of the different places that involve the pregnancy, you can see a decrease in the amount of group B strep that's present versus the control. Again, just by using these oligosaccharides from human milk. Okay, so this was pretty cool to get this result. And Rebecca and Professor Gaddy are currently undergoing round 2 of this study. And we hope to have something out in the literature, within the next 3 to 6 months. All right, so I'll close just by giving a couple of really fun slides and talking about one more project just for one slide. We only got 3 left, so no one has to tap out. But I remember when I was a postdoc, I was practicing for my job talk, and my advisor, Professor Danishevsky, who's to the far right, told me, you're going to give your practice talk on the Columbia lab side. So catch the cab over there from Sloan Kettering and go ahead and set up. So I walk into the room, and it was a firing squad because 3 famous professors, Koji Nakanishi, Ron Breslow, and Gilbert Stork, who have all recently died, unfortunately, they were sitting in the room, right? So I go in there to give my practice talk, and I'm giving it to all of these people who are National Academy members and who are borderline or should have been Nobel laureates. And it was really helpful because they grilled me. They asked me a lot of great questions, but some of the most profound are actually still sticking with me today. So Professor Breslow asked me, what's the endpoint to this project, right? When does this end and you move on to do something else? Professor Stork said, and when it's all over, what are you actually going to do next? And then Sam came in and said, well, just ignore them. You can do whatever you want in science because you have no bounds. Just make sure you don't synthesize stuff just to stick it in the freezer. He is a person who fundamentally hates the idea that organic chemists would make things and not use them for something. Okay, so I think in our group, we pride ourselves on not doing that. Things that we make, we actually figure out what they do. But to the point of Professor Breslow and Professor Stork, when is it over? And so for us, I don't know when this actually ends. I think it ends when we can put human milk oligosaccharides in a human's mouth to cure some type of illness that they have. Okay. And so one final thing that I'll talk to you about is irritable bowel syndrome. We call this irritation of the gut. This is something that every human experiences at any given time. 1 out of 3 people on Earth has some type of gut inflammation or irritation. If you're unfortunate, some people have Crohn's disease or ulcerative colitis, which are very extreme versions of this. And yeah, 20% of people, right, have one of these diseases. So these are things that are debilitating and they're very painful. So ultimately, what we wanted to see is whether or not we can use milk oligosaccharides to prevent gut inflammation in an adult. And so this is work that's done with Dr. Fong Yan over in our medical school. It turns out we can test this in a mouse model, right? Is it possible to prevent inflammation of the gut? What happens is that we use dextrin sulfate sodium. This is a chemical that mice are allergic to. It's very toxic to their epithelial cells and causes them to have inflammation that in most cases looks like ulcerative colitis or Crohn's disease. The way this experiment works is that for 7 days, we're going to study a cohort of mice. For 6, we just dump milk oligosaccharides in their drinking water, for 6 days. At day 4, we start to give them the poison. And then at day 7, we sack, and then we evaluate their epithelium to see whether or not we prevented inflammation of the gut. For 5 mice who we only gave water, they have no inflammation. That's shocking to no one because we're not allergic to water. For the mice that have dextrin sulfate sodium treatment, it turns out that about 4 of these mice actually had Crohn's disease. The one had severe ulcerative colitis or inflammation. And then finally, we have 5 mice where we gave them this toxin, which clearly causes inflammation in the presence of milk oligosaccharides. And it turns out that we're able to prevent inflammation in 4 of the mice. I can go ahead and spike the football and show you the test subjects. It turns out that on the far right, These are the mice that were just given water. So these are your standard gray Jackson lab mice. On the far left, we have the mice that were given the poison in addition to milk oligosaccharides, okay? So this is dope, right? Even though these mice were poisoned, they still weigh about 2 to 3 grams heavier. They have these shiny white coats. And so you can clearly see from a phenotypic standpoint, the power of these milk oligosaccharides to promote health. Now, the question is, how did we save their lives? Well, it turns out this was all related to manipulating the microbiome. So what we found out is that the mice that were given milk oligosaccharides, we basically upregulated the amount of anti-inflammatory bacteria that were present in their gut, and we significantly decreased bacteria that are pro-inflammatory. And so we're basically just building up a strong epithelial bacterial community. And so if you want to read more about this topic, we have a paper coming out in the series. We have another on chemotherapy or preventing the damage of chemotherapy using HMOs that was just accepted. A lot of cool stuff coming out of the group when it comes to application. And so with that, I'll stop talking and just give, credit first and foremost to the trainees. When you start a new lab, all of the senior faculty tell you, it only takes one student to get you tenure. But I don't like to think of it like that. And I think that's kind of insulting. What I like to think of it as is, it can be intimidating and scary to be an assistant professor because you feel like you're alone. But in reality, the students will save you because, if you're in danger, they will save you. If you're going to have a ridiculous idea, they will tell you. They run in here left and right, and they're always phenomenal. The people highlighted in red are the ones who were the major players when it comes to the Human Milk Project, although other people have contributed. We've had a large number of undergraduates in the lab who were phenomenal. And of course, the bulk of people who've worked in this group work on small molecule or carbohydrate total synthesis. I wasn't able to talk about their work, but it's not because it's not important. It's super critical to what we do. It just didn't fit in today's story. Maybe you'll hear me talk about it later. And then, of course, I want to thank our collaborators and our sources of funding, because people don't have to fund you. And when they do so, you owe them good results. And my team has been very good at doing that. So with that, I'll just shut up. And if you have any questions, I'll take them.
Awesome. Well, thank you so much for that great talk. Lots of cool information there, lots of cool stories. I'm going to go ahead and check in our Q&A here and see what we have. Okay, so we'll start out with one from our Q&A. Are there any dangers associated with potential HMO supplementation as preventative therapy?
Yes, when it comes to HMOs, they're completely non-toxic, right? Babies consume, on the low end, 8 grams, on the high end, 20 grams per day. And so when it comes to toxicity, the answer is no. When it comes to allergies, the answer is maybe. So there are a number of companies who are trying to make these compounds and stick them in human milk. The problem is not all babies consume the same compounds because all babies' mothers are different. So it is a scenario that if a baby drinks some formula that has one of these synthetic compounds in it that their own mom doesn't make, that they could have some type of allergic reaction that hasn't been teased out well. But from the angle of toxicity, these are 100% non-toxic. I've given consulting trips and watched people eat these things in their coffee instead of regular sugar, which is another weird story for another time, but they're not toxic.
Awesome, thank you. Next question. You presented a lot of collaborations. How are these collabs perceived by the higher ups when you're in the process of trying to get tenure?
Yeah, that's great. So Vanderbilt is a place where when I came here to visit, the provost at the time, Provost McCartney, was like, this is a collaborative environment. If you are going to be an organic chemist who just makes things and sticks them in the freezer, and he's in the know, he's a psychologist, so he understands what we do. He told me not to come here if I was going to be that type of organic chemist because he didn't think there was a place for that anymore. So when it comes to collaborations, they are rich at Vanderbilt. You hear the word interdisciplinary and collaboration almost too much, I would say, on this campus. So here is true. If somebody has something, right, if you want to bring it together to form a collaboration, it is very much appreciated here and it is expected. So we're a little bit different compared to some more traditional types of departments.
Okay, great. Next up, We have, since the makeup of oligosaccharides vary from person to person, how would you, one, identify the single or more likely ensemble of oligosaccharides needed for a favorable result? And two, how do we make this on scale for therapeutic or supplemental use?
Yeah, so my former trainee and now my current, great friend, Kelly Craft, would, throw up if she heard you ask that question. So what Kelly discovered was, there's 200 compounds possible in milk, but 50% of the mass of compounds are only represented by 10 structures. So Kelly, because she's brilliant, came in one day and was like, dude, I'm about to replicate human milk because I'm going to take the most abundant compounds and combine them and then just have super sample. Well, when she did that and she went to go assay it to see how powerful it was, it turns out it wasn't powerful at all. And so we don't know the answer to which compounds are most important in what ratios and in what combinations. So that answer is still TBD. When it comes to production, there are currently about 5 or 6 companies that are making swimming pools of this compound in the microbial cell factory. So you can manipulate E. coli or yeast to produce these compounds tonnage. Are these the most abundant compounds in milk? Yes. Are they the most abundant compounds that are being produced now by all women? The answer is no. So we still don't have ways to produce compounds that all women universally produce, just because we haven't been able to produce and generate the enzymes that are needed to make the glycosidic bonds. But companies like Nestle or Glycome are producing these compounds at scale. So far, we can do that to about 3 or 4 out of 200.
Okay, next up, we have great talk. I think you mentioned that species with larger litter sizes have fewer oligosaccharides. Have similar trends ever been observed in people who have twins or multiples?
Yeah, so mice are a good example, right? If you take 2 mice and you put them in a room and you come back at the end of the year, you got 30,000 mice. And so when you look at mouse milk, they only have 2 oligosaccharides. And they're not interesting. Humans produce them in small quantities, but they don't really have any activity. Mice don't have a long lifespan, so all of the stuff fits. When it comes to people who have multiplets, it turns out that their milks are exactly the same as women who have singlets. Milk is phenomenal. We've had a sample from a mom from North Korea, a mom from Somalia who was malnourished, and a mom from Calabasas, California. And pound for pound, all of their milk was identical in amount of antibodies present, oligosaccharides. So what I'm getting to is that your body will sacrifice you in order to make sure that the baby is fine. It's crazy. So even if you're malnourished or you have the best diet on earth, those 2 women will have equal important and potent milk for their own baby, because that's how human evolution works.
Interesting. Okay, we got one more that came in here. Did Rebecca also test bovine milk in preventing strep colonization?
So we have not, and that's an important set of experiments. Rebecca won't be able to do it because she's staring down paper number 20 in a graduation. So she ain't doing it. Yeah. Sabrina, though, may do it, and that's an important one because Group B strep kills more cows than humans. And it's believed that human beings engaged with Group B strep because it made the cow to human jump. So that is an experiment that we need to start doing to see whether cows have inherent protection against Group B strep, because then maybe we could use those sugars. But we have not done that just yet. And Rebecca has half of her body out the door.
Well, congrats to Rebecca. I'd like to close it out here with one, I guess, non-sciencey question. Earlier in your talk, you mentioned, not just learning to be a scientist, but also how to exist as a Black scientist. So, you were fortunate that Amanda Bryant Friedrich, right, was present for you there. I was fortunate that you existed at Vanderbilt, but unfortunately representation at the professor level is, it's still very limited. So in that vein, what advice or suggestions would you have for students of color that are trying to find a mentor or, support in an environment that's predominantly non-students of color or other, I guess, marginalized groups?
Yeah, it's tricky. So, there's a couple of matters of recourse. When I was a graduate student, there were only 2 Black students in the department out of 140, me and Shanessa Atkins. I was the first Black faculty member to join this department. So when I was a student, man, it was like just weird, man, because I'm from Detroit, where like everybody looks different. There's everyone in Detroit, but that wasn't the case on this campus. So my first sort of pit stop was across the street to Fisk and Tennessee State and Meharry, and I met a lot of people over there to see, because it's flat out, it's different. Even now, the things that I have to deal with in my family and personal life, so now there's other Black colleagues. But before Renee got here, Renee Robinson, who's the president of Novachet, there wasn't anybody who I could talk about, things that go on in my life where they could actually empathize or understand what I was going through. So that was out. When I was a student, I went to HBCUs. Everybody doesn't have those or access to those. So the next best thing for me was actually the social sciences and humanities, because although STEM is not diverse at the moment, sociology has beyond parity, right? In our sociology department here, they're like 35% people of color. Anthropology is like 51%. So yeah, so you can reach out to people in social sciences and humanities to get people who are going to speak the same language. And at least what I see in modern times is the amount of emails and text messages I get from people who I have no clue who they are. But it's from a seminar or somebody saying like at UCLA, hey, my advisor, can you position me to a Black faculty member to talk to? And they get in contact with me that way. And people like myself, Richmond Sarpong, right? The list goes on, highly receptive to that happening. So yeah, just, seek out the people who you need, I think.
Awesome, that's great advice, and we appreciate you making yourself available to the community there. So with that, we are at time here. So thank you again, Steve, for an awesome talk. We appreciate you sharing not just your science, but also some of your story with us here. And I'm going to go ahead and end the seminar there. Thank you.